All right, in this problem, we've got a 2 kilogram spool on this rod, and the coefficient of static friction between the rod and the spool is 0.2. Okay, so in this position shown, what's the minimum speed so that the spool does not slip down the rod? Okay, so what we're going to do is we're going to draw our free body diagram. Okay, and in our free body diagram, I have the weight of the spool, 9.8 times 2 kilograms. I have friction. Friction is going to be moved up the rod because I'm trying to avoid it slipping down the rod. So friction goes up at 0.2 times the normal force, and then I've got a normal force, again, acting perpendicular to the rod. The coordinates I'm going to set up are based on the fact that I know it's accelerating towards the center of the circle. Okay, and we set our coordinates up based on what we know about acceleration. And my acceleration accelerates to the left towards the center of that circle. Okay, so we set up our normal axis, basically horizontal, and then we've got our b-axis, which would be our z-axis shown here straight up. So first things first, I need to use basically trigonometry to figure out the radius of curvature, which would be the perpendicular distance from the z-axis to my sleeve S, which is going to be essentially 4/5 times the 0.25 meters. So it's going to be 0.2 meters away from the z-axis perpendicularly to the sleeve. So that is my radius of curvature that I'm going to use to find my normal acceleration. Okay, so I sum the forces in the normal direction. Okay, that's the horizontal direction. So I'm going to have 3/5 times my normal force. Okay, then I'm going to have my friction force, which will be 4/5 times 0.2 times the normal force. So again, that's 4/5 for the horizontal. Okay, that's going to equal my mass, which is 2 kilograms, times my acceleration, which is v squared over rho, which again we found to just be 0.2, which is the perpendicular distance from the z-axis out. Okay. I can also sum the forces in the b direction or the z direction, as the picture shows. Okay, so that would be 4/5 times the normal force and 3/5 times the friction force, both of those acting upward. Okay, and then I'd have the weight of the object, 2 times 9.8, acting straight down. Okay, now there's no acceleration up and down. Okay, because I, again, don't want it to slip up or down the rod, so there'll be no acceleration here. So it's in static equilibrium vertically, and then horizontally it's got the centripetal acceleration v squared over rho. So from this bottom equation, I can find the normal force, knowing the normal and the friction and the weight. I can figure out the normal force, plug that into the top equation, and solve for the velocity, which would be 0.969 meters per second. So that's the velocity needed to keep that from slipping down the rod.